If you've shipped ordinary software, you already know the reliability playbook. You write tests, watch dashboards, and use logs to explain what broke. Artificial intelligence agents or AI agents change one important part of that playbook. Ask the same question twice, and you may get two different answers even when nothing crashes. So we need to judge behavior, not just uptime. Observability records what happened inside a run. Evils are repeatable tests that score the result. Together, they give us one useful equation: reliability equals observability plus evals. We'll build that equation one piece at a time with concrete examples and no machine learning background required. First, what exactly is an agent? In this tutorial, an agent means a language model running in a loop with instructions and tools. A language model is software that interprets and produces language. Let's make the agent's parts concrete. Part 1 is the system prompt, written instructions that define the agent's job, its boundaries, and the rules it must follow. Part 2 is its tools, ordinary functions you choose to expose: search an orders table, look up a customer, issue a refund. Part 3 is the model. It reads the request, chooses a tool, reads the result, and decides what to do next. That repeated cycle, decide, call, read, decide again, is the agent loop. It ends when the model concludes that the task is complete. And here's the testing challenge: the path is chosen while the agent runs. Two runs can take different paths and still reach a good answer. That variable path exposes the problem with an exact match test, a check that passes only when the output matches one expected value exactly. With a conventional function, the same input usually produces the same output. That's the assumption behind a simple assertion. Ask an agent the same question three times, though, and you may get three differently worded answers that are all correct. The wording changed. The opposite failure is more dangerous. The agent can reply fluently and return a 200 status code, while the answer itself is wrong. A status code can't catch that. We need evidence of what happened inside the run and a way to judge the quality of the result. Those two needs give us the equation: reliability equals observability plus evals. Observability means recording what the agent did, the prompt it followed, the tools it called, what came back, and the final response. An eval, short for evaluation, is a repeatable test that scores how good that behavior was against criteria chosen in advance. You need both. Observability without evals gives you evidence but no verdict. Evals without observability give you a bad score but no explanation. So we'll start with the evidence before adding agent specific records. Let's look at the signals already on your dashboard. For a conventional service, that dashboard probably begins with three familiar signals. Error rate tells you how many requests failed. Latency tells you how long they took. Availability tells you whether the service could be reached. Logs record events, metrics, summarize numbers over time, and traces connect the steps of one request. Together, they show whether the system operated. Keep all three for an agent. It can still throw server errors, become slow, or go offline. But a healthy service can still produce a bad answer. To see that failure, the trace has to capture the agent's whole run. A trace is the ordered record of one request as it moves through a system. For an agent, that record needs more detail than a single log line. Think of it as a timeline with nested steps. We begin with the customer's request, then preserve everything that shaped the answer. First, record the system prompt and its version prompts change. So the version tells you which instructions govern this run. Second, record the tools that were available. The agent can only choose from what you exposed, and that list changes as you ship. Third, record every tool call, its arguments, its position in the sequence, and how often it ran. Fourth, keep each tool's raw response. A wrong final answer often begins with a tool that returned stale, empty, or malformed data. Fifth, record the observable model outputs at each step, including its tool selections and final answer. You need the decisions the application can actually inspect. Now, a bad run isn't a mystery. You can open the trace, follow the sequence, and find the first step where reality diverged from the plan. That same record also supplies the evidence for an eval. Now we can define how the verdict works. That brings us to the second half of the equation, evals. The easiest mental model is an AI unit test. It serves the same purpose in your workflow with one important change. A unit test gives code a fixed input and compares the result with an expected value. The assertion passes or fails. An eval gives the agent a fixed task, then applies a rubric. A rubric is simply a written set of criteria for what a good result must do. The rubric produces a score, often from 0 to 1. You then choose a threshold, the minimum acceptable score, to turn that result into pass or fail. The rest feels familiar. Keep a suite and run it in continuous integration or CI, the automated checks that run on every code change. Block a merge when quality drops, and add a case whenever a bug reaches you. The difference is what you test. An eval measures behavior produced by your prompt, tools, data, and model working together. So, what should it score? We can answer that by mapping familiar service signals to the additional signals an agent needs. Alongside error rate, track task failure, the request completed without an exception, but the agent still didn't accomplish the user's goal. Latency still matters, but now it includes the whole loop, every model call, every tool call, and every retry. Availability expands too. Your service may be up while a model provider is down, rate limited, or unavailable in one region. Cost becomes a runtime signal. Models charge for tokens, the small chunks of text they read and produce. So, cost per successful task belongs beside latency. Then come quality signals with no direct equivalent on a conventional uptime dashboard. They judge the answer and the action path. We'll focus on three. Answer relevancy asks whether the response stayed on the question. Groundedness checks whether its claims have evidence. Tool sequence accuracy checks whether actions happened in the right order. Let's take them one at a time. Answer relevancy measures whether the response addressed what the user actually asked. To judge that, compare the user's request with the agent's response while considering the system prompt that defines the agent's job. Suppose I ask what is an apple and receive a polished paragraph about bananas. The paragraph may be true, but it isn't relevant. That failure is called drift. The agent wanders away from the request or answers a nearby question that feels easier. The system prompt matters because relevance depends on scope. A support agent giving unsolicited legal advice has left its assigned job, even if the advice sounds plausible. A score near 1 means the response stayed on task, but relevance alone can't tell us whether its claims are supported. That's groundedness. Groundedness measures whether the answer is supported by the information the agent was actually given. It uses the request, response, and system prompt plus one crucial input, retrieved context, meaning the source material available during that run. That context can include documents, database rows, search results, and tool responses. It is the evidence the answer should stay anchored to. The evaluator breaks the answer into claims and checks each one against that context. Is this statement supported, or did the agent invent it? An unsupported claim is a hallucination, language that sounds confident and useful but isn't backed by the available source material. So the distinction is clean. Relevancy asks, did you answer my question? Groundedness asks, what evidence supports that answer? A response can be relevant but invented, or well supported but about the wrong topic. That's why the scores are separate. Actions introduce a third question: did the agent use its tools correctly? Tool sequence accuracy measures whether an agent called the right tools in a safe and correct order. It matters as soon as the agent can take action. This evaluation focuses on the trace of tool calls rather than the polish of the final sentence. Consider a refund. The expected sequence is find the customer, load the order, verify eligibility, and only then issue the refund. Now imagine the agent finds the customer, loads the order, issues the refund, and checks eligibility afterward. Its customer facing reply could still be relevant and grounded, but the money moved before the safety check, and only the tool trace reveals that failure. Compare the actual trace with the expected sequence. Were all required tools called? Were unnecessary tools added? Did the required order hold? Once an agent can act, this is a system safety problem, not just a writing problem. To score it repeatedly, we need trusted examples of correct behavior. Those trusted examples are the final missing piece. Evaluators often call them ground truth, the reference used to judge a result. In a unit test, ground truth is the expected value you write down. 2 plus 2 should equal 4. For an agent, correct behavior is often richer than one value. So you build a golden dataset, a reviewed collection of realistic tasks and correct behavior. Each task records the qualities of a good result, required facts, forbidden claims, and the tool steps the agent should follow. Build it with subject matter experts, meaning people who understand the real job. That might be a clinician, a risk analyst, or a support lead. If you need more coverage, create synthetic cases, meaning artificial examples based on real patterns, then have an expert review a sample. Otherwise, you may only be testing your own assumptions. Start small, 50 cases you genuinely trust will reveal more than 5,000 cases nobody has read. Then grow the set from production. Every investigated failure can become a new golden case. That's where observability begins to strengthen the eval suite. At this point, a practical question appears: who owns this work? In conventional software, a separate quality assurance team or QA team could compare a build with a written specification and report whether it matched. Agent quality is harder to hand off completely. A reviewer needs the prompt, each tool's expected inputs and outputs, the source data, and the intended behavior to judge a run well. So the engineers building the agent should own the executable evals, add them beside the feature in the same change just as you add unit tests beside code. Subject matter experts remain essential. They define what correct means. Put the pieces together and you get a loop your team can start using with the next change. First, something changes: a system prompt line, a tool, a data source, or the model version. Next, the eval suite runs that version against the golden dataset just like another test job in CI. If a score falls below its threshold, the change doesn't ship. The quality check becomes a deployment gate, just like a failing test. If the version passes, it goes live and every production run writes a trace. Your team reviews failed or suspicious runs. Each confirmed problem becomes a new golden case, making the suite more useful over time. Now the circle is complete. Traces feed evals, evals gate deployment, and production reveals the next cases worth testing. Let's return to the equation one last time, now that every term has a concrete meaning. Reliability equals observability plus evals. Observability is the trace, the prompt version, available tools, tool calls, tool results, and observable outputs from the run. Evils are the verdict, scores for relevance, groundedness, and tool order compared with trusted golden cases and enforced with thresholds. The discipline isn't new. You still collect evidence, write tests, gate changes, and learn from production. The system under test is simply more variable. So start with three moves: capture a complete trace, build 50 trusted cases, and run those three scores in CI. Then reliability becomes something you can inspect, measure, and improve.